Okay, so I want to give you a little guided tour of section 3.3. 3.3 deals with Cramer's rule, and it's yet another way to solve a system of equations. Now, you learned in the last class, and you've practiced this in your most recent homework, you've practiced finding determinants. And you know how to do cofactor expansion from section 3.1. And section 3.2, you learned how properties of determinants really help you find determinants of matrices. And it's particularly helpful for when matrices are not sparse. A sparse matrix is a matrix with a lot of zeros. A dense matrix is a matrix that has a lot of non-zeros, okay? And the properties of determinants, the row operation properties, are tremendously helpful. And the idea is to try to get the matrix through row operations into echelon form, which would be triangular form, since we're talking about a square matrix here when we do a determinant. You get the matrix in triangular form using the row operations, and then computing the determinant is easy. Okay, and of course you have to follow the rules before you get there, right, for determinants, but it makes it easy. How many love determinant properties? How many are loving those? I'm sure some of you are. Okay, Sega likes it, Diva Heart. Wow, lots of people. Christy, Solman, Robin. All right, great. Kevin, wonderful. It's interesting. Christy has a red heart, and the rest of you have thumbs up. So thumbs up are good, but I didn't know they had a red heart as emoji. I'm gonna have to keep that in mind. Okay. Oh, Kevin. All right. Kevin found it. All right. Matthew has an arm flex thing. Okay. I'm gonna have to broaden my horizons here. All right. So let me go ahead and bring up the ebook. Okay, textbook. And let's talk about Cramer's rule. Okay, Cramer's rule. All right, one moment here. Okay, just closing a few files out here, so I got a little bit more manageable layout here. Okay, wonderful. So let me see here. Let me blow this up a little bit. Okay, so Cramer's rule, and I'm looking, let me see here, get my little pen out here, is section 3.3. Cramer's rule is needed in a variety of theoretical calculations. For instance, it can be used to study how the solution of AX equals B is affected by changes in the entries of the vector B. And you had a problem like that in your past homework when you had an inverse that was, you had a matrix A that was essentially almost non-invertible. And you saw that in that situation, when you have a high condition number, that can greatly affect the solutions if you alter that constant vector B even just a little bit. But what we want to do is we want to show Cramer's rule here. Cramer's rule says if you have an invertible square matrix, then for any vector B in Rn space, the unique solution X of the matrix equation AX equals B has entries given as they show you here. So the X sub I, which, X sub 1, X sub 2, X sub 3, okay, X sub I would be equal to the ratio of the determinants. The numerator determinant is this determinant of the square matrix A sub I of vector B. Now, what does that mean? All right, they show it above here. When you take the matrix A, and you notice this matrix A consists of column vectors of A. But if you replace the ith column vector of A with that constant vector B, okay, that for your system of equations, that's called A sub I, the matrix A sub I of vector B. I just call it A sub I B. So the solution to a system of equations now can be found this way. X sub I equals the determinant of A sub I B divided by the determinant of A. Okay, and the question is, first you might want to ask, well, how did we get this? How do we get this? Well, let's look at the proof. The proof's on the next page. It's not hard to show it. What you do is, of course, as you know, the columns of the matrix A we denote by the vectors A1 through AN. And the columns of the identity matrix I sub n can be denoted by E1, vectors E1 through En. Okay, so remember, instead of vectors I, J, and K, and so forth here, we use E1, E2 up to En. It's more convenient because, we only have 26 letters in the alphabet, whereas if we use the E notation for these unit vectors, we can have as many as we want. So if A times X equals B, the definition of matrix multiplication shows that if we multiply A by the identity matrix I sub X, so what is that? That would be where you take the identity matrix and you replace the ith column of the identity matrix by the vector X. So the matrix A times this I sub I X matrix would just be then, using the definition of the matrix multiplication, it would be the matrix whose columns are A times E sub 1, A times E sub 2, then you got the A sub X, and then, and then more columns, and then finally A sub En. All right, and but the matrix A times the vector 1, 0, 0, 0, 0, and so forth is going to be A1. If you take the matrix A and multiply it by that unit vector E sub 1, you're going to get the column vector A sub 1. That's what you'll get. If you take the matrix A and multiply it by X, you're going to get, of course, that equals the B vector. The matrix A times E sub n times that unit vector would be A sub n. And so that gets you, that by definition is the matrix A sub I B. So you have a equation here, a matrix equation that says, hold on here, that says A times I sub IX equals A sub I B. But what we can do is we can take the determinants of both sides of the matrix equation. Well, the determinant of a product is the product of the determinants. So the determinant, let me just hold on here. One moment here. What I'm trying to do is erase some of my markings here. I guess I have to do it separately, but that's okay. Just so I can be clear. No big deal. Okay, so A times that identity matrix, I sub IX, that's not the identity matrix, exactly. It's not the identity matrix. It's A times I sub IX equals A sub IB. But now what we do is we take the determinant of the left side and the determinant of the right side of that matrix equation. But the determinant of A times I sub IX is just the product of the determinants. You learned that. the determinant of A times B is the determinant of A times the determinant of B. So now we have then this equation, but it's a scalar equation now, right? The determinant of A times the determinant of I sub ix equals the determinant of A sub ib. But the determinant of I sub ix equals x sub I. Okay, because basically what is I sub ix? It's a matrix where along the diagonal you have ones. Okay, that's the identity matrix, except in the ith spot you have an x sub I. So the determinant of I sub ix equals x sub I. And therefore, determinant of A times x sub I equals the determinant of A sub ib. And if you divide both sides by determinant of A sub ib, you'll get the Cramer's result, the Cramer's theorem. X sub I equals the determinant of A divided by the determinant of A sub ib. All right, are there any questions on the derivation? It was done, Cramer lived in the 1800s, I believe, but it's not really a hard proof, but he's famous because of it, right? So, are there any questions before we move on? All right, well, let's move on then. Let's move on. So we want to solve, I always make this mistake. I click, hold on here, I got to go up. You have to be very careful when you move on this thing. All right, so let me just go down a little bit. Okay, so in this example, we want to use Cramer's rule to solve this system of equations. Okay, take a look at it. In one moment. Yeah. No, it's been beeping a while. We're good. We're good. Okay. Okay. So, I mean, I think example one, it's pretty self-explanatory what you're seeing there. But I mean, are there any questions? Let me see. We got a few. No, this is the practice problem, Matthew. I'm not gonna. This one is This one, I think, like problems that I consider more difficult. I normally then do examples formally, but this is, I think, pretty straightforward. Look at the example and tell me if you have any questions. I mean, you have it right here. You have it right there. So the coefficient matrix A is 3, -2, -5, 4. The matrix A sub 1b, okay, this matrix here, what they did was they replaced the first column with the 6, 8, which is that vector B of constants from the system above. And then the -2, 4 they leave alone. And then A2b, the second matrix, what do they do there? Oh, they keep the first column of A there, 3, -5. And then the vector B is, they replace the second column of A with the 6, 8. So the determinant of A is 2. And here's x1 and here's x2. I mean, are there any questions on that? It's okay if they are. Okay, Matthew's good. Any questions from anybody else here? Okay, thank you. All right, Christy's good. All right, all right. Well, then let's just continue on here. So they talk about applications to engineering. Okay, so a number of important problems, particularly in electrical and engineering control theory, can be analyzed using Laplace transforms. If you take differential equations, which is Math 282, I teach that. Actually, I'm the coordinator for that course. If you take differential equations, you'll learn about Laplace transforms. The next example illustrates the type of algebraic system that may arise when you have a parameter. So here, in example 2, they say, consider the following system in which S is an unspecified parameter. Determine the values of S for which the system has a unique solution. Okay, so here's your 2 by 2 system, or it's 2 variables, right? So, I mean, you know, here's the system. Here's A. Here's A1B. Here's A2B. Are there any questions on that? How they're getting those 3 matrices? All right. Well, so remember in Cramer's rule, the denominator is determinant of A. So in other words, when you solve x sub I is, so the variables are all written as a ratio of determinants. But every one of the variables in the denominator, you have the determinant of A. So if the determinant of A is 0, then you won't have a solution. Okay, you will not have a solution. And that makes sense because if in Cramer's rule, A has to be invertible. Well, if the determinant of A is 0, then A is not invertible. All right. So what they do is they set up in the problem what x1 and x2 are using Cramer's rule, and then in this problem, hold on, I went too far as usual. Let me go back up. In this problem, they're saying that you'll get solutions so long as S is not equal to plus or minus 2, because that would make the determinant of A 0. Okay. Yes, Matthew, quick question about the second example. Yes, yes. Let's see, the B is in column 1 for A1B. That's correct. That's correct. And then, yes, that's right. So for A1B, the second matrix here in the solution, they replace the first column of the matrix A with the B. A sub 2, B, they replace the second column of matrix A with the vector B. All right, all right. So everybody's reasonably comfortable? Okay, all right, all right. All right, moving on here then, moving on. So the book talks about a formula, another way to get A inverse, using something called the adjoint of A. And I'm sure that does have importance, but I'm not going to focus on that. You won't see a problem like that in your homework, but just be aware, theorem 8, that if you needed to find the inverse of A, there's like you learned the algorithm to find the inverse of A. You learned an algorithm, but there's another way to get the inverse of A. It involves cofactors of the matrix A, and it's just another way to find an inverse. But I'm not right now worried about that. Let me see here now. One moment here. They do talk about how it's used in theoretical calculations. There's always these numerical notes that they talk about, numerical notes. And they're saying Cramer's rule is not as efficient as, for instance, the row operations in the numerical notes, but you can use it for theoretical purposes. But let's move on here. All right, so determinants is area or volume. Okay, so how many maybe in Calculus 3 learn that, I want to be careful here, that the, hold on here, one moment. So in Calculus 3, how many learn that the absolute value of the cross product of two vectors in R2 space is equal to the area of a parallelogram? How many maybe have learned that if they've taken Calculus 3? Does anybody recall a theorem like that? Okay, a few of you have. Very good, very good. Well, yes, and so absolutely, absolutely. And all right, so very good feedback here. Thank you, everybody. Wastina Sega, Divahar, Matthew Sega. So here we are actually going to learn that if you have a 2x2 matrix in Theorem 9, if you have a 2x2 matrix, then the area of a parallelogram determined by the columns of the matrix A is actually the absolute value of the determinant of A. Okay, in other words, the determinant of A, if you show you here a geometric proof of this, but want to be a little bit careful. So like if you have like here the parallelogram in figure 1, the parallelogram is a rectangle. And the rectangle, they take the two sides of the rectangle are determined by the vectors A0 and 0D. So they have a vector on the x-axis, A0, okay, and then they have a vector on the y-axis, 0D. Well, the determinant, if you form a matrix A, okay, you form a matrix A whose columns are those vectors, the determinant of that matrix is equal to A times D. And if you take the absolute value of A times D, in this case, since A and D are positive, you wouldn't need the absolute value, but the determinant is equal to the area of the rectangle, base times height, base times height. Okay, they did talk. Matthew is right. In the homework, they did go into a little bit of some examples with parallelograms and so forth. So you're a little bit familiar with this. And what they do in the book is they talk about they have a lot of words here. They have a lot of words, okay? And I want to just show you why this is true in general. Why this is true in general. So what I want to do, I'm gonna show the part where the area of a parallelogram is equal to the absolute value of the determinant of the matrix A, where A consists of the column vectors. The column vectors of A are the vectors that form the sides of the parallelogram. I want to show that. The parallelepiped, obviously, the part where if you have a 3x3 matrix, the volume of the parallelepiped determined by the columns of the matrix A is the absolute value of the determinant of A. That's harder to show. Okay, but the book does talk about things on the following page. But I want to just keep things simple here. Let me go ahead to the whiteboard. Okay, and let me see here. All right, and I'm going to try to draw this the best I can. Hold on here. Let me put it in black, part of this in black. Okay, so I'm going to draw two axes here. And let's see here. Actually, what I might do is I might, what I think I'm going to do is let you work on the section 3.3 for a little bit. And while you're doing that, I will, I mean, I have a document here. I have something I made up that has like what I was going to draw on it. And I think it'll be more efficient if I just write it down on paper and then scan it and upload it. So let me give you like 15, 20 minutes here for you to work on the section 3.3 exercises that are due on Thursday. One moment here. Let me just make them available here. One moment. So I deactivated them. I didn't want anybody working on them now, but I'm assigning the 3.3 exercises. And let you work on that a little bit right now. Okay, I'll stop the recording.